Welcome to my online course in linear algebra for undergraduate mathematics. Today we are going to discuss diagonalizable operator. Let T be a linear operator on finite dimensional vector space V, then T is said to be diagonalizable if there is a basis P for V, is vector of which is a characteristic vector of T, that is eigenvector of T. Next is matrix of diagonalizable operator. Let T be a diagonalizable operator on n-dimensional vector space P and B equal to alpha 1, alpha 2, alpha n, Bn ordered basis for P such that each vector alpha I is a characteristic vector of T, that is T of alpha I equal to Ci alpha I, where Ci is the eigenvalue corresponding to the eigenvector alpha I ranges from 1 to up to n. Then is T alpha I equal to Ci alpha I can be expressed in terms of the basis element as given below. That is T of alpha 1 equal to C1 alpha 1, which is equal to C1 alpha 1 plus 0, so, 0 alpha 2 plus .0 alpha n. T of alpha 2 is equal to C2 alpha 2 equal to 0 alpha 1 plus C2 alpha 2 plus .0 alpha n T of alpha n is equal to Cm alpha n 0 alpha 1 plus 0 alpha 2 Cn alpha n. The matrix of T relative to B is given by the coefficient of alpha I in the right hand side of the expression, that is as given by this matrix. T of B, matrix of T relative to B is equal to C1 0 0 0 0 C2 0 goes to 0 0 Cn, that is this is n by n diagonal matrix. Next is a remark. If V is n-dimensional vector space, then T is diagonalizable if and only if T has n linearly independent characteristic vector. A linear operator T on n-dimensional vector space Vf is diagonalizable if and only if its matrix A relative to any order, this is P of P, is diagonalizable. Next is diagonalizable matrix. A matrix over a field F is said to be diagonalizable if it is similar to a diagonal matrix over the field F. That is, a matrix A is diagonalizable if there exists an invertible matrix P such that P inverse A P is my diagonal matrix T. Next is example on diagonalizable operator. First example, let T be a linear operator on R3 which is represented in the standard basis by the matrix given by this. Prove that T is diagonalizable. Let us denote the given matrix by A. Then the characteristic equation of A is determinant of A minus xi is equal to 0. Here A is my 3 by 3 matrix. So we consider the identity matrix I to be a 3 by 3 matrix. Put the value of A and I in this equation. Then simplify, we will get this one. That is, from the diagonal element of A, we will subtract x. Then apply the transformation C1 tends to C1 plus C2 C3. We will get this one. Since in place of -1 minus x, we can write minus within bracket 1 plus x. So taking this common from the first column, the given determinant will reduces to this determinant. The given determinant this reduces to this determinant. That is minus 1 plus x minus 1 within bracket 1 plus x in the determinant 1 4 4, that is 1 3 minus x 4 1 8 7 minus x. Applying the transformation R2 tends to R2 minus R1, R3 tends to R3 minus R1, we will this determinant reduces to equivalent determinant, this one, that is 1 4 4 0. The if we subtract this row from this one, then it will be 0. It will be minus 1 minus x, then it will be 0. Again, if we subtract this from this will be 0, and this will be 4, and this is 3 minus x. Now expanding this determinant along first column, we will get second order determinant, this one. So cross multiply, we'll get this equation. That is, if I take minus common, it is 1 plus x into 3 minus x. This will be 0. So this minus minus will be plus, that is 1 plus x, 1 plus x. 3 minus s is equal to 0. Therefore, root of the characteristic equation here, minus 1 minus 1, 3. Therefore, the eigenvalue of the matrix A are minus 1 minus 1, 3. Let x be the characteristic factor corresponding to the eigenvalue minus 1. Then by definition of eigenvector, if x is eigenvector of a matrix A corresponding to the eigenvalue of minus 1, then we can write this Ax equal to minus 1. Since minus 1 is a numeric value, we associate the identity matrix of the order equivalent to the or equal to the order of the given matrix, then the vector. So bring the right hand side to left hand side. That can be written as a minus minus 1 into I we into x as given by this equation. So minus minus become plus. Put the value of A and identity matrix, then simplify, we will get this equation. That is, we add 1 to the diagonal element, we will get this matrix. Since the right hand side is 0, so this system of equation represent the homogeneous linear equation. So solve this system of equation by method of solving homogeneous linear equation. The equivalent system of equation are, that is, we will find the rank of the coefficient matrix by echelon form. Make this 0 and this 0 with the help of proper row transformation as given by this. Here system of equation, rank is 1 and there are 3 equations. So this system of equation is consistent and has infinite solution, and number of independent solution is number of equations minus rank, that is 2. 3 minus 2, 3 minus 1 equal to 2 independent solution. And reduced system of equation is write this system of equation in matrix form. Multiply this row with this column, we will get this equation and equate it to right hand side, remaining will be 0. So we will get only one equation, that is minus 8 into x1 plus 4x2 plus 4x3, which is equal to 0. Now from this equation, take 4 comma, then divide the equation by 4, we will get minus 2x1 plus x2 plus x3 is equal to 0. In the next step, bring this 2x1 to right hand side and divide the equation by 2. We will get x2 plus x3 by 2 is equal to x1. If we take x2 equal to 1 and x3 equal to 1, then 1 plus 1 is equal to 2. 2 by 2 is equal to 1. Our x1 is also 1. That is, x1 equal to 1, 1, 1 is my one eigenvector. Another eigenvector is obtained by taking x2 equal to 1 and x3 equal to minus 1. Then x1 is my 0. Since no, x1 and x2 are not a scalar multiple of each other, so these two vectors are linearly independent solution of linearly independent eigenvector corresponding to eigenvalue x equal to 1. Next, eigenvector corresponding to eigenvalue 3 is given by a minus 3ix. Again, ax equal to 3ix. Bring 3ix to left hand side, I will get a minus 3i. Take x common, then it will be x equal to 0. A minus 3i within bracket, then x equal to 0. Put the value of a and identity matrix I of order 3. Then subtract 3 from the diagonal element of A. we will get this matrix. Since the right hand side is 0, so this will represent a system of homogeneous linear equation. System of linear homogeneous equation. Now solve this by the system, by the method of solving homogeneous linear equation. Find out the rank of the coefficient matrix. Find out the rank of the coefficient matrix. Find out the rank of the coefficient matrix by applying proper row transformation as given in this. Here we have found that there are two non-zero rows. That is rank of the coefficient matrix is 2. Therefore, the system of equation are consistent and has infinite solution, and the number of independent solution is 3. Number of equation minus rank of the matrix, that is 3 minus 2 equal to 1. Independent solution. So write this system of equation in equation form, that is multiply minus 12 with x1 add up with 4x2 plus 4x3, then equate it to 0, then 4x1 minus 4x2, it is 0x3 will become 0, that is 4x1 minus 4x2 equal to second 0, and last equation is just equation of 0 coefficient in x1, x2, x3. So this will give you these two equations. Take the common from first equation, we will take 4 common, then it will be minus 3x1 plus x2 plus x3. Divide the equation by 4, you will get this equation. And in the second, take 4 common and divide it by 4. We will get it x1 minus x2 is equal to 0. From this equation, I will get x1 is equal to x2. Put this x1 is equal to x2. I will get minus 3 x2 plus x2 is equal to x3. That is x3 is equal to 2x2. That means if I take x1 is x2 equal to 1, x3 is my 2. Therefore, x3 equal to 1, 1, 2 is my eigenvector corresponding to eigenvalue 3. Next, we consider a matrix P consisting whose column are the eigenvector of A. That is, first column is this vector, second column is this vector, linearly independent eigenvectors of A. So third column is this one. If you expand P, you will, if you find out the determinant of P, you will get it is 1 and not equal to 0. That means P is my invertible. An inverse of P is given by 1 by determinant of P. Xy of P is equal to this one. Also, column of P are linearly independent. These are linearly independent eigenvector. Linearly independent eigenvector. So column of P are linearly independent. That means P is diagonalizable. Correspondingly, my linear operator T is diagonalizable. And diagonal form is given by P inverse AP. Put the value of P inverse, that is this, and A and P. We will get this one. Now multiply. You can multiply this three matrix in any order, since all these are 3 by 3 matrices. So multiplication is possible. I am multiplying considering the first I take the last two matrices, then get the resultant, then product resultant with the first matrix, we will get this diagonal matrix. This is the required diagonal form. Next, prove that the matrix A equal to 1, 2, 0, 1 is not diagonalizable over the field C. The characteristic equation of A is determinant of A minus xi equal to 0. This implies if we put A equal to this matrix, and here A is a 2 by 2 matrix, put the identity matrix of order 2 by 2, that is 1, 0, 0, 1, and subtract it from A. That means from the diagonal element you can subtract x, that is 1 minus x, 2, 0, 1 minus x. Then expand the determinant, I will get this one. 1 minus x squared, 0. Cross multiply this with, then cross subtract the cross multiplication of this. This is 0 into 2 will be 0. So the root of the equation are 1, 1. Eigenvector corresponding to eigenvalue 1 is given as this. A minus ix, put the value of a, then subtract identity matrix, then put x. Here, identity matrix is 1. In place of x, I have 1. So 1 minus 1, then 1 minus 1, remaining element will be black as it is. So this is 0 to 0, 0, x1, x2, 0, 0. Again, this is a homogeneous linear equation. Solve this homogeneous equation. Here rank is 1 and number of equation is 2. So the system of equation is consistent as and has infinitely many solutions. Well, there is 2 minus 1 equal to 1 linearly independent solution. That is, put x from this equation, I am getting x2 equal to 0, x1, put x1 equal to any value 1. So x equal to 1, 0 is the linearly independent eigenvector of A. Since we are not getting two different linearly independent eigenvector for A, so A is not diagonalizable. Correspondingly, linear operator is not uh, diagonalizable operator. These are your home assignment. With this, your fourth unit is completed. Next Thursday is a doubt clearing session on Unit 4. You should come to the doubt clearing session and clear your doubt. With that, I would like to conclude. Thank you.